This week we start stochastic gradient descent algorithm. The stochastic gradient descent algorithm is very related to the recent deep learning optimization process. There we basically, since we have too many training data set, we cannot compute the fully computed gradient, the exact gradient vector. Instead, we have to randomly sample a small subset of data set and then calculate the loss function or objective function and then compute the gradient for the subsampled data set, not the entire data set. Okay, so in that case, we do not compute the fully computed exact gradient. Instead, we compute stochastic random gradient vector. But in practice, with the stochastic gradient descent, we can achieve very nice optimal point. And we actually have very nice performance with many different architectures. So it is very important to understand why stochastic gradient descent algorithm works very well in practice and when we can improve the performance even more than now. So this is the example of stochastic gradient. So basically, most of the case of deep learning, we have this kind of loss function. Every data point have to compute the loss value, which define fix. So here the I indicate the data point index. So more precisely, this x is a parameter, and the data point define a different function because your loss value depend on input and output of your sample data or your i's data point. Okay, so to optimize the loss function for your entire data set, you have to optimize this objective function, which is basically empirical average of your loss function for each data point. Okay, and most of the case fi are different each other, and it is very difficult to find out the optimal point that minimize this loss function, even that is not convex. Okay, so we basically use gradient descent approach because gradient descent approach can at least find local optima with any type of function in many cases. But when you compute the gradient for this objective function, true objective function, basically we have to compute the gradient of each data point and then averaging the entire gradient vector over whole data point. When there are a few data points, like 1,000 data point, then that is fine. We can compute the 1,000 data point gradient vector, and then we can averaging them. That is fine. But the problem is recently we have millions or billions data point. Okay, so to calculate the millions of or billions of gradient vector for each data point, we have to wait a lot of time. Okay, so that is not practical at all. So we have to find out some another approach. Okay, so that is the problem of pure gradient descent algorithm or vanilla gradient descent algorithm. Okay, so people use stochastic gradient method, which sample item uniformly at random so that the expectation of your sampled gradient is equal to gradient of your full function. Okay, so when you sample a data point uniformly random, then each index I sampled with probability 1 over n. So the expectation of gradient of fit, the sample to index x, that is equal to 1 over n summation I1 to n gradient of fi x. Okay. So this is called stochastic gradient or stochastic gradient oracle. So for given input point x, the oracle output a random vector gx such that expectation of gx belong to the gradient or subgradient set. Okay. For random input point x, the oracle output a random variable gx such that expectation of gx given x for given input point x belong to the subgradient of fx. So essentially, the stochastic oracle means the observed vector is not deterministic value, so we cannot access to the full information of your current point gradient vector. We cannot observe the full information of that, but instead we have some random observation of which expectation is equal to their gradient. Okay, that is very nice property to optimize your objective function. So with the stochastic gradient oracle, we can learn gradient descent algorithm, and that is called stochastic gradient descent. So like gradient descent, we update xt plus 1 from xt minus step size gamma or learning rate gamma times the stochastic gradient oracle gt. So here gt is equal to gxt, and expectation of gxt is equal to the gradient or subgradient of your true objective function f at point xt. Okay. There are some assumptions for a simple analysis. So I will analyze the convergence speed of the stochastic gradient descent algorithm, and I will analyze the performance of the stochastic gradient descent with respect to the some properties of stochastic first order oracle. So to do this, I will firstly assume that f is alpha strongly convex and beta smooth, so that the problem is very easy to analyze. And also I will assume that the variance of your stochastic gradient is upper bounded by sigma square. Okay, so the gt minus the true gradient, so the stochastic oracle minus the true gradient is upper bounded by some constant, okay, in terms of the Euclidean norm scale, okay, on average. So basically, the performance of stochastic gradient descent very rely on the sigma square value, the upper bound of the error, expected error. This is quite trivial. Why? So when we have very high variance, essentially, although we can achieve the true gradient with infinite number of observations at the same point, because we have the expectation equal to the true gradient. So when you collect infinite number of observation at the same point xt, you can basically obtain the true gradient vector. But this is not allowed in practice, and also we always move some point xt every time. Okay, xt plus 1 is not equal to xt. So essentially from the gradient descent or stochastic gradient descent update, we have to make up the error of each step due to the gradient estimation by stochastic gradient descent. But when the sigma square is very high, this is very difficult because we have a huge error, which can make some diverging trajectory due to the high noise. Okay, so in the analysis, we will analyze what is the convergence speed and convergence accuracy with respect to this. Okay, with respect to the sigma scale. Right. So from simple analysis, you can easily check this. The expectation of gt minus gradient of fxt normed square is equal to expectation of gt normed square minus gradient of fxt normed square. Okay. So now let's analyze the convergence rate and the convergence accuracy of stochastic gradient descent algorithm. Yeah, from beta smooth, we have this. From beta smooth, fxt minus fxt plus 1 for given xt is greater than or equal to expectation of gradient of fxt transpose xt minus xt plus 1 minus beta over 2 xt minus xt plus 1 normed square. This comes from the beta smooth. Okay, and this is equal to expectation of gamma times gradient of fxt transpose gt, which comes from the definition of SGD, minus beta times gamma square 2 times gradient gt normed square. Okay, this also comes from the definition of the gt, the stochastic gradient descent. And since this term is not random variable, not random vector, so we can bring it to the outside of expectation. So we have gamma times gradient of fxt normed square. Now let's use the fact that gt, the expectation of gt is equal to the gradient of fxt. So we have gamma times gradient of fxt normed square as the expectation of this part. And then we just write down the notation expectation of gradient of gt normed square at point for given xt. Okay, right. So from the definition of sigma square, you can upper bound this one, right? So we have basically have expectation of gt normed square minus gradient of fxt normed square is upper bounded by sigma square. Okay, so which means expectation of gt normed square is upper bounded by sigma square plus gradient of fxt normed square. So we can replace this term using the gradient of fxt normed square and sigma square. That is the result. Okay, gamma here, and 1 minus beta gamma over 2 times gradient of fxt normed square minus beta gamma square over 2 times sigma square. Okay, and from alpha strongly convex, we have this result. Actually, I provide the proof of this inequality week 2, maybe. Yes. So using this inequality, we can replace this part. We can replace this part by 2 alpha times fxt minus fx star. Okay. From this, we have this inequality. expectation of fxt plus 1 minus fx star for given xt is less than or equal to fxt minus fx star minus gamma times 1 minus beta gamma over 2 times gradient of xt norm square plus beta gamma square over 2 times sigma square. Okay, it's very good. So from the alpha strongly convexity, we have this inequality by replacing this part by this. Okay. So we have very nice result. So without this, that is actually exactly the same with the convergence analysis for alpha strongly convex and beta smooth objective function with gradient descent algorithm with step size gamma. Okay, but we have this because of stochastic gradient property, because of the variance. Okay, so from this inequality, actually, we can roughly understand the convergence behavior of your gradient descent algorithm with stochastic gradient. When sigma square is very high, you cannot guarantee fxt plus 1 minus fx star is less than or equal to fxt minus fx star when this value is very, very high. But when sigma square is not such high, then you can guarantee fxt minus fx star less than or equal to fxt minus fx star on average, in expectation sense, by controlling gamma. Okay, so here gamma is just multiply with gamma, but here we multiply gamma square. So with sufficiently small gamma value, you can ignore this part compared to this. Okay, so basically this value is strictly less than 1 and this value is negligible. So from that you can decrease fxt minus fx star by using stochastic gradient descent algorithm. Okay, more precisely, using this form, you can iteratively calculate this inequality. Fx capital T minus fx star is equal to this. This is less than or equal to this. Okay, I just write down the previous inequality. And iteratively calculate fx capital T minus 1 minus fx star, fx capital T minus 2 minus fx star, and so on. In the end, you have this. This sum comes from the gradient descent analysis for alpha strongly convex and beta smooth case with gamma step size. But because of sigma square variance term, we have this additional term. Okay? So when you have high sigma square, what's wrong? You have high error. You have problems. You cannot find out the exact solution X star using gradient descent algorithm, stochastic gradient descent algorithm. But again, note that here you have gamma square, but this has only gamma. So when your gamma is sufficiently small, so much smaller than sigma square, then basically you can ignore this part. Okay, but the problem is this term also increase as you decrease gamma. Okay, when gamma is too small, then this value is too close to 1. So which means you cannot decrease fx0 minus fx star with capital T number of iteration. So you have to control the gamma value very well. So let's consider two cases. Before, without stochastic, we set gamma is equal to 1 over beta. Like in that case, let's set gamma equal to 1 over beta. Then, using 1 over beta, we have this. 1 minus alpha over beta power to capital T times fx0 minus fx star. That basically equal to the case without stochastic. But because of the variance of your stochastic gradient, you have additional term. So you cannot convert to the exact x star, but you have this additional error term. Okay, so with 1 over beta step size, that was the optimal step size for vanilla gradient descent algorithm. Your loss function dropped very fastly with speed of 1 minus alpha over beta capital T, but it does not convert to x star. It does not convert to the optimal point, but it converts to some biased point. But essentially, it oscillates nearby the optimal point when you look at the trajectory of your stochastic gradient descent algorithm. Okay, actually, you can simply check the trajectory of stochastic gradient descent with constant step size. In that case, I'm pretty sure you observe very oscillated the trajectory. So some people use this type of step size, time-dependent step size. When you know the end time, capital T, you can basically set gamma is equal to 1 over square root of capital T. Then when capital T is sufficiently large, so you have enough iterations, basically you have this error rate. This is very nice. Beta sigma square over 2 alpha square root T. So basically you can convert to the true optimal point x star when capital T go to infinity. When capital T go to infinity, so you have infinite number of iterations, you can convert to x star with speed of 1 over capital T. Okay,